Hey, hi everyone. Yeah, my name is Aaron Goldin, and I'm going to be presenting our work on time and voltage domain load models for appliance level simulation and control. So I guess this is a bit of a change of pace, or at least a change of scale. We're zooming in to the appliance level here, and to sort of briefly describe the motivation for this, I'd like to first sort of go over the traditional grid architecture depicted here, which is based on the centralized control of dispatchable generation. But as we all know, this is changing as we introduce more and more renewables to the grid. The variability of supply needs to be met with new grid services to match supply and demand. Of course, generation isn't the only thing that's changing. When we focus on residential loads, the load itself is changing. We see the introduction of electric vehicles and solar generation and battery storage behind the meter in homes. Furthermore, appliances themselves are changing. Internet of Things and smart appliances allow us to network with them and potentially control their power consumption as well. So this changing landscape in residential loads presents an excellent opportunity to use them as a distributed energy resource. Of course, one of the major challenges here is coordinating the vast number of disparate and relatively small resources to actually provide any sort of grid service of value. One of the potential approaches to this challenge is to utilize local controllers. So the idea here is that some local intelligence, say at an individual household, is handling the control signals to the appliances or the batteries or so on, and then communicating more broadly with the coordinator, receiving, say, a generalized power set point command. A common feature of these local controllers would be to broadcast back to the coordinator often like a feasibility range for control or some kind of forecast for power consumption in some time domain in the future. And so in this context, the appliance load model now is really critical to the local controller. If this house level forecast is going to be of any use, that power forecast has to be accurate. And to sort of demonstrate why we need to improve appliance load models, we can kind of see this with the example of an air conditioner. Air conditioners are a pretty common high energy load. The plot on the top left shows measured air conditioner power versus time. This is for a whole day. And the plot on the bottom left shows a really common model that we use in grid simulation software and often also to formulate controls for aggregate air conditioner control in the research. And what we can kind of see from this model, this is the second order extended thermal parameter model results for the same temperature profile as the measured data. We can see that this model, first of all, does a very good job of estimating the duty cycle behavior. And we can kind of see how, if we're interested in the aggregate of, say, thousands of air conditioners, this model is sort of perfectly accurate to capture, perfectly adequate to capture that behavior. But if we're interested in the power consumption of, say, an individual household, we don't get the benefit of averaging out, say, thousands of simulations. We can see if we zoom in even further on the power consumption of an individual on cycle. So these are all plots of power consumption versus time and voltage. This is for a single air conditioner. The different colors show the various temperatures, outdoor temperatures, but we can see that there's a really strong dependence on time and voltage as well, with power varying between 600 and 900 watts, depending on the state. So if we rotate this plot around, we can see that these dynamics are actually quite significant if we're interested in a forecast, say, over the next few minutes. This plot shows 3 or so minutes of power consumption. So for this work, we focused on two main categories of residential loads. The first being ceramic heating elements. These are commonly used for space heaters, They're also used in various appliances, kitchen appliances like coffee makers and so on. They're popular because ceramic heating elements, their resistance increases as the temperature increases. So they're sort of inherently stable and safe. The other main type of load is vapor compression cycle loads. These are essentially heat pumps like refrigerators and air conditioners. So as you can see, we've sort of honed in on these two load types because they actually exhibit significant dynamics at the time scales that we're interested in. And we also focus on them because they make up a fairly large fraction of residential energy consumption. So when we look at the breakdown by residential load type in the United States, we see that space heating, refrigeration, and air conditioning actually make up well over a third of all residential electrical energy consumption. So to kind of summarize here the problem and objectives, we're looking for effective power forecasts at the level of an individual home. And to do this, we need more detailed models than what we typically use for power systems. Conventional ZIP models or extended thermal parameter models don't capture these coupled time and voltage domain dynamics, which actually can be quite significant. So the objectives here are to develop simple physics-based models that capture this observed behavior, identify the measurements and the tests that we need to do in order to learn the parameters of these models. And we developed some preliminary parameter estimation tools, and then we verified the accuracy of these models. To carry out the test, we built a test setup using custom power electronics that gave us control over the voltage to specific loads and allow us to record at high resolution and high time resolution the voltage and current to the load, and then record that data. So our approach here is kind of an iterative approach. Once we set up the experiment and develop the code to run these tests, we take a look at this data and kind of try to figure out what physical models might work to describe this behavior, develop that physical model, and then see how we can actually learn the parameters from the measurements we have available. So in this case, we're focusing on just voltage and current measurements, and then iterate on this to develop a suitable parameter identification methodology. Before I dive into the specifics of the two load categories we focused on, there are still a lot of residential loads where the traditional models work just fine. Here we show error in real and reactive power for various common load types like fans and lights. And these loads don't exhibit significant dynamics. So if we excite the RMS voltage, even in a pretty broad frequency range or periods from 100 seconds to 1 second, the RMSE errors are actually quite low in both real and reactive power. However, when we look at ceramic heating elements, we see that the nonlinear temperature resistance relationship causes interesting dynamics here. So the plot on the left is a power response to voltage shift. So on the very top is power, the middle plot is voltage, and then the bottom is current. And we can see that the RC time constants actually vary quite dramatically depending on what voltage we're at. And we can see how this manifests behaviorally. The plot on the top right shows startup transients that depend not only on the voltage, but also on the initial temperature of the heating element. The model that we found that describes this fairly accurately has sort of two main components. First, we use an RC equivalent circuit to model the temperature of the heating element relative to an ambient temperature. We tested both first and second order models. Both work well. Second orders, as we'll see, slightly more accurate. The other key component of this is to characterize the heating element resistance as a function of steady state power. This can be represented as a two-part exponential function. This has 7 parameters. And as we can see, the measured versus model impedance is actually fairly accurate using this approximation. To learn these models, we used a mixed learning approach to learn the correlation between steady state power and impedance of the element, we use nonlinear least squares plus steady state data. And then to learn the remaining dynamic parameters, these are the thermal RC time constants, we used particle swarm optimization. So this animation on the top right shows in blue the measured power as in response to a sinusoidal voltage, RMS voltage excitation. And the orange line is the model as we iterate through the particle swarm and hone in on the correct RNC values. And the plot on the bottom right shows a comparison of errors. So we see a significantly reduced error using the dynamic models, especially as the excitation frequency goes up. And this makes some intuitive sense. It should be noted here, I think it's worth discussing that these parameters, we're only learning them from the voltage and current measurements. So in a sense, the parameters form a kind of black box to enable us to simulate these power trajectories. But we don't actually know what the temperature, for instance, we don't actually know what the temperature of the heating element is, but we don't really care. We just care about the power trajectory. And so this physical model allows us to, say, input sort of meaningful initial conditions for the particle swarm, and so on. Moving on to refrigeration cycle loads. These are generally characterized by a hysteresis thermostatic control. When the controller turns on, it turns on an induction motor. These motors typically have a large inrush transient, which we don't model. It's a very short transient. Now, the interesting thing is once the motor kicks on, the power tends to vary quite dramatically. It usually decays. Sometimes it increases before it decays. And then there's also a voltage dependency, although this voltage dependency doesn't really interact with the time dependency so much. And we can kind of see how this looks as we rotate a plot of power versus voltage and time. These blue lines are constant voltage tests, and the black line shows power consumption as we vary the voltage sinusoidally in time. To model this, we used a standard vapor compression cycle model. This model assumes isothermal condensation and evaporation and isenthalpic expansion at the expansion valve. The temperatures of the evaporator condenser, we use first order RC thermodynamics. But the key to this model really is equating the mass flow rate to some key parameters. In this case, condenser parameters. So the speed of the motor, the volume of the compressor, and the compression ratio of the compressor, as well as the pressure and temperature of the input and output refrigerant. That mass flow rate then can be equated to a torque if we include some additional friction terms and the enthalpy change of the refrigerant across the compressor. This is sort of the key here, because once we have a torque term, we can use a very simple motor model to equate that torque to voltage and current. So to learn the parameters of this model, we used a two-stage particle swarm optimization. So the key insight here is to split the parameter identification based on the meaningful errors here. So we have two stages, one that optimizes for cycle duration, and one that optimizes for the actual power trajectory or the RMSE error in power during and on cycle. And so we identified the parameters that are sort of sensitive to each of these objective functions. So it turns out that the condenser thermal impedance and mass are really what determine the cycle duration. And then the remaining parameters tend to have a more significant effect on the power trajectory during the on cycle. We can kind of see how this plays out in an animation where we show the iterations of the particle swarm optimization. We can see how when the particle swarm is varying in the time domain, we're optimizing over cycle duration, and then in the power domain, we're optimizing for the shape. And we can see how it converges on a fairly accurate solution. So this just shows some measurements versus prediction for some refrigerators. Here we used an hour of training data. And we can see that even with only an hour of training data, we can get to extremely low RMSE errors. To conclude, we demonstrated that very key high energy loads do exhibit dynamics that are not captured in the traditional load models. We focused on vapor compression cycle loads and ceramic heating elements. We demonstrated that simple physics-based models can capture these dynamics, and that it is possible to run parameter estimation routines based solely on voltage and current measurements, which makes this possible to potentially implement for a local controller in the context of distributed energy resource control. Thanks everyone for listening. So let me.
Okay, thank you, Aaron. So far, I don't see any question. If I remember well, you mentioned in the paper also an application like a CBR for reducing the load, no? Feeder load.
Right, exactly. So the context here, I didn't have time, but I think that's a great question. So like I mentioned, the context here is to provide predictions for a local controller, but another key concept here is that we have control of the appliances. And there are a lot of ways we can do that. We can do that with simple contactors to turn them on and off. Another thing that we're experimenting with at Stanford is the use of voltage control to power or to control the power consumption of these loads. So for instance, a heating element, you have full control over how much power it's consuming if you can control the voltage to the element. Even things like refrigerators or air conditioners, you can control their power within a certain range, right? You have to worry about not getting toward the stall voltage, but yeah, you can control power using voltage control. So that's another application for this modeling work. I'm seeing some questions in the Q&A here.
Yeah.
Okay, Nawaf Nazir asks, would these parameters translate to devices from different manufacturers and different devices of different sizes? Oh, that's a great question. So broadly speaking, because we used a physics-based model, the parameters for, say, like all air conditioners in a certain power range are similar, but certainly not the same. And in fact, the parameters can vary quite a bit even within appliances of exactly the same make and model. Like, so for instance, how much refrigerant is in the refrigerant loop actually changes a lot of these parameters. So the idea is that you actually would learn this model online, and we demonstrated this in the paper somewhat, that you can actually, based on actually fairly short amount of training data, learn the model. So that's a great question. You would have to learn the parameters for each appliance under test. Okay, oh, I'm getting some more questions here. Mods asks, can you clarify on the order of the models? It seems like they are all second order. Who will provide these models, parameters, manufacturers or OEMs? Okay, I see, that's a similar question. Yeah, yeah, we use sometimes first or second order thermal models. The idea again is that we can learn them just from the voltage and current measurements. So if we have a trajectory of power over time, we can in fact learn those physical parameters live. Okay, next question. Adil asks, in load control schemes, what inputs will your models require? Are on-off signals enough, or voltage current measurements also required? That's actually a really great question. So for this paper, we okay, so we do need voltage and current measurements. And in this paper, we assume that we can control the voltage, so we can excite the voltage to the load, so in a sense to perturb it to get a training data set. It is also possible to simply just use the turn on and off transients to learn the models. But yeah, the voltage and current measurements are required for these models. Okay, Alexander asks, do you think that your model may be over-parameterized? Oh, that's also a great question. The answer is almost certainly yes. The reason that we keep it over-parameterized is that all of these physical parameters have some meaning. And as we, for instance, if we have access, and this is sort of out of the scope of this paper, but it is important that, for instance, if we have access to temperature data, then it allows us to quickly adapt the model that we learned maybe with just voltage and current data and improve the same model if we add additional measurements. Okay, last question here. Patrick asks, could you explain how do you design the input signals and how do you control the environment? Okay, that's also a good question. The input signals are, we just use sinusoidal RMS voltage excitations just so we can look at the response kind of in a frequency context, although it doesn't actually seem to matter too much what they are if you have a sine input or a square wave input. How do you control the environment? Okay, that's also a really good question, although I think we're running out of time here, so I might answer that offline. So yeah.
Okay, it's up to you. You can answer very briefly.
Okay, very briefly. So we actually don't. We are measuring like the ambient temperatures, but the models assume just a sort of a nominal value. And what we find is that the parameters kind of adjust. So even if our assumption in, say, the ambient temperature is wrong, the model parameters are sort of adjusted such that because like the previous question sort of mentioned, it's sort of over-defined, right? So even if we're incorrect in our ambient temperature, there is a solution that accurately predicts the power trajectory. But then again, if we have access to an ambient temperature measurement, that can then be incorporated into the learning of the model. So I hope that answers the question.
Okay.